So welcome to the presentation for the paper Conformant Synthesis for Koopman Operator Linearized Control Systems. And as a motivation for the topic, let me begin with a quote which says, "All models are wrong, but some are useful." And of course this guy is right. So I think as we all experienced in our careers as scientists, we often have a nice model of our system. However, if you then measure data from the real system always behaves a little bit different. So often that's not a huge problem. For control, for example, we take measurements, right, to control out these model uncertainties. However, I'm coming from the formal verification community, and there it's actually a huge problem, because if we want to design a formally safe controller, then we want that this controller is safe for the real system and not just for the model we have. Luckily, there's a solution to that, which is called conformant synthesis. And here the idea is to add a non-determinism to the model, so that it over-approximates all behaviors of the real system. So for example, we can add non-determinism in form of a process noise on the differential equation and in form of a measurement error on the output. And then if we predict with an uncertain model, we get, instead of a single trajectory, we get a reachable set out of it. And then this reachable set should contain all measurements that we took from our real system. And if this is the case, then we say the model is conformant. And that's what our paper is about, conformant synthesis. So we want to automatically determine the amount of uncertainty we have to add to our normal model so that it's conformant with the set of measurements we took from the real system. And in particular, we focus on a special type of a nominal model, which are Koopman linearized models. So let me motivate Koopman linearization first. So often we have a quite complicated nonlinear system dynamics, and therefore it's quite hard to get the control inputs that fulfill a certain control task. So the idea of Koopman linearization is to apply a nonlinear state transformation to transform the system state to a state where the dynamics can be approximated very well with a linear dynamic system. Then for linear systems, we have a lot of sophisticated control techniques. So it's actually quite easy to get the control inputs to fulfill a certain control task. And then hopefully, if our Koopman linearized model is close enough to the original nonlinear system, then these control inputs will be very similar, but easier to compute. So that's basically the trick for Koopman linearization. The big question, however, is how to compute or how to determine this nonlinear state transformation defined by the observables, which results in a space where the dynamics is linear. And multiple different methods have been proposed. So one popular method is polynomial observables. So we just compute polynomial transformation of the system states and then get a higher dimensional space. Of course, also neural networks have been used for that. So neural networks are great to learn arbitrary nonlinear functions. So they are of course also great to learn this nonlinear transformation that is required to obtain this linearizing Koopman space. And the third very popular method are random Fourier features, which are basically trigonometric transformations of the state, where the frequency and the shift are randomly drawn from certain distributions. And as we know from the Fourier theorem, arbitrary signals can be represented by a linear combination of trigonometric functions with different frequencies. That motivates why random Fourier features might be a good choice for this nonlinear transformation. And the great thing about our conformant synthesis approach is that it actually supports arbitrary types of observables, so you can actually use all of these together with our approach. So once we determined the observables we want to use, what is the overall process to get the nominal model using Koopman linearization? So we first start with an original nonlinear system, then simulate it to get some trajectories which we can train on. Then we apply our observable function to transform these trajectories to this higher dimensional Koopman space, and then apply dynamic mode decomposition to identify the dynamics of the linear system in this space. Let me mention that for neural network observables, we actually do basically the training the observables and dynamic mode composition kind of in parallel or together, because we want to learn observables that lead to a good linearizing dynamics. For the other types of observables, that's actually sequentially as depicted here. So we first decide on an observable and then just kind of hope that the space we found has a linear dynamics. And the great thing about this process is, since we're working with data anyway, we actually don't even need a nonlinear system model. So there's no requirement for a normal model because we can directly identify the Koopman model from the measurements we have from the real system, which is one of the great advantages of the Koopman framework. So that's basically how to calculate the nominal model using Koopman linearization. Now finally to our approach, which is to, once we got this nominal model, how to make it conformant with all measurements we have from the system. And for conformants, there are basically two big groups or big types of conformants, which are trace conformants and reach set conformants. So for trace conformants, we basically try to match the trajectories that we measured by determining suitable values for the non-determinism, just the process noise and the measurement error in our case. And we basically solve an optimization problem to determine the minimum amount of uncertainty so that we can match the trajectory. And for Koopman operated linearization, since the dynamics is linear, this optimization problem actually boils down to a linear program or quadratic program, depending on what we want to optimize, or which loss function we want to minimize, basically. For reach-set conformance, on the other hand, we basically compute the reachable set of the non-deterministic model and check if our measurements are contained inside an inner approximation of this reachable set, as it is depicted on the right side here. And if this is the case, we say that the model is conformant. And both methods have advantages and disadvantages. So trace conformant kind of gives the best possible solution because we directly optimize to get the minimum disturbance to match the trajectory. And that's not necessarily the case for reach-set conformance because reachability analysis, we cannot compute the exact reachable set. So we have to compute an inner and outer approximation, which comes with some approximation error. With reach-set conformance, we therefore in general don't get the tightest possible solution or best possible solution. However, a disadvantage for trace conformance is that we have to solve this optimization problem for each trajectory, and we usually have a lot of data, right? So that even so, these optimization problems are linear or quadratic programs that can become very costly. And that again is then the advantage of reach-set conformance. So first, we often can group certain trajectories together there and handle them together. And second, reachability analysis, especially for linear systems, is super fast and often more efficient than solving these optimization problems. So that's an advantage of reach-set conformance. And you already see here that basically the advantages of one method are the disadvantages of the other one. So the natural thing to do here is to combine these two methods together. That's actually exactly what we do for our approach. So we basically take out a trajectory from our set of measured trajectories, and then first apply reach-set conformance to check if this trajectory is already conformant with our model. If this is the case, then we don't have to do anything, right? Because the model already explains this trajectory, and we're good. If it's not yet reach-set conformance, then we apply a trace conformance to match this trajectory and to determine the values for the non-determinism that we need to match this trajectory. What we basically get out of this optimization problems are a lot of points for this non-determinism of the model, so for the measurement error and for the process noise. And this basically forms a point cloud. However, for the model, also for the final model, so that we can use it for reachability analysis or for the safe controller synthesis, we have to represent this uncertainty with a set. So what we have to do is basically enclose this point cloud we get out with a set representation. And there are different possibilities, the easiest one being intervals. So we basically just compute the bounding box of our point cloud, which is very efficient to compute. However, as we also see in the picture here, the real set of uncertainty we get out is usually not an interval. So the interval enclosure also comes with a certain over-approximation error. On the other extreme are polytopes. So if we compute the convex hull of the point cloud, we get the tightest convex enclosure, which can be represented as a polytope. However, convex hull computations are quite computationally demanding, especially for high dimensions. And also the resulting polytope we get out might be very complicated, so might have a lot of vertices or a lot of half spaces. Often a good trade-off between these extremes are sonotopes, which are very compactly, or can be represented very compactly, are often relatively efficient to compute, and as we see in the picture, often they are a little bit tighter than the interval over approximation. Often a good trade-off. This was basically our approach. Finally, some numerical examples. So we tested our approach on certain benchmarks, which are electric circuit, a robot arm, and F110's race car. And for all of these, we have basically measurement or to have measurements from the real system. And the electric circuit consists of 3 states, which are internal voltages and currents. The robot arm has 12 states, which are the angular positions and velocities of the 6 joints of the robot. And the F110's race car has 4 states, which are the x and y positions, the orientation, and the velocity of the car. We took the measurements we had from these models, and what we did first is we identified a model using Koopman operator linearization. And as I mentioned earlier, the great thing about our approach is it supports arbitrary observables. So we, to demonstrate that, we took 2 different types of observables, which are random Fourier features and neural network observables. And the ones we identified as a nominal model, we wanted to check its accuracy. So that was basically shown in the first column, the average prediction error of the Koopman model compared to the original measurements. And we see this errors for all benchmarks about 6%. And so it's quite low, which means that basically Koopman operator linearization is very well suited to identify models for these systems, even though the systems are quite complicated, like this 6 degree of freedom robot arm. So once we had the nominal models, we then applied our conformant synthesis approach to determine a conformant model. And after that, of course, we wanted to evaluate how good how accurate our conformant model is. So what we did is to compute the reachable set of the conformant model for all measurements, and then as a metric took the average volume of this reachable set. And that's shown in the second column, and we see the average volume is very small, which means our conformant models are quite accurate for all of these systems. And finally, what's shown in the third column is the computation time that's required to make 1 second of data conformant. And we see for the robot arm, the F110's race car, this value is actually lower than 1 second, which means our approach is even real-time capable. So we could even run conformant synthesis on the real system, and every time we get in a new trajectory, we can update our model to make it conformant with this trajectory, which I think is also a great advantage. Only for the electric circuit, the computation time is larger than 1 second. The reason for that is that this benchmark has a very high sampling frequency for the measurements. However, it's also just about 2 seconds, and our approach is currently implemented in MATLAB. So if we could go for a C++ implementation, maybe we could even make this benchmark real-time capable. We also compared our approach to other approaches for conformant synthesis. In particular, for the robot arm, we compared to an approach for linear systems, and for the electric circuit, we compared an approach for hybrid systems with linear dynamics. And what's shown in the picture is basically measurements and the corresponding reachable sets of the conformant model. And we see in both cases the reachable sets for our approach are tighter. And this can be basically attributed to 2 facts. So first of all, Koopman linearization usually gets a better approximation of the system dynamics than this linear approach used for the robot arm and the hybrid model used for the electric circuit. And second, our approach uses trace conformance, where the other conformant synthesis approaches uses reach-set conformance. So basically our approach also computes the best possible solution, while the other approaches come with some over-approximation. And finally, we took the conformant model that we constructed for the F110's race car, and combined it with a safe MPC control approach, to obtain a safe controller, and then run that on the F110's race car. And as you can see here, we then can control the race car safely, so that it safely reaches the goal set shown in green, while avoiding this obstacle shown in orange. How this control approach works is here that it optimizes, or model predictive controller works, is that it optimizes over the reachable set in real time. And that's only possible because the Koopman linearization results in linear dynamics where reachability is very fast. So this wouldn't be possible for nonlinear dynamics, which is another great advantage of the Koopman framework. So that is results in this linear dynamics where control is very fast and often quite easy. Okay, so to summarize, we presented the first conformant synthesis approach for Koopman operator linearized models. And what's very awesome about this approach is that we can directly apply it to data we measured from the real system. So there's actually no requirement for a symbolic model. You just need to measure data from your real system, apply our approach, and you get a Koopman a conformant model out, which you can use for controller synthesis. Also, our approach supports arbitrary observables, is real-time capable for most systems, and as we have seen in the final experiment, it's possible or very well suited, or the resulting model we get out are very well suited to design safe controllers. So thank you very much for your attention, and I'm looking forward to your questions at the conference.